like this?
Yes.
Great. So you have to recognize that this is integration by parts, like you said. They may not tell you on the exam.
Yeah, she said she's gonna throw a bunch of integrals at us, and we're gonna have to figure it out what we're gonna use to solve
Yeah.
it.
Now you should anticipate like one of each type. So if you check the box on one, probably isn't going to be there. The other one wouldn't be that. So here you got to figure out u and dv. This is the type where it's a polynomial times a trig function. This is always x, the polynomial is u, and the dv is the cosine 5x dx. So whenever you get an integral that's a polynomial of x, like x squared, whatever it is, times a sine, a cosine, or an e, it's always this path that we're about to go down. Okay, so your du is dx. Your v, because you're integrating, is 1/5 sine 5x. Any questions on that?
Not right now. No.
Okay, so we get uv minus integral v du. You got to know that. That's where you just start mapping these things you just found. That's your u, that's your v. So it's x times 1/5 sine 5x minus the integral of 1/5 sine 5x times dx. So on the left, you are done integrating. You don't have to integrate, you just simplify 1/5 x sine 5x. The one on the right, though, you do have to find the antiderivative of this, and it's the antiderivative of sine is minus cosine, so that becomes a plus. Because of this 5x inside here, you get another 1/5 out in front. And you can't forget that plus c. Super critical.
All right. Why didn't you have to take the integral of the first one, or is that just the formula?
That's the uv. Yeah, that formula, that first one you don't integrate.
Okay.
Because it's already been taken into account by this by parts method.
Okay.
Okay, so you got 1/5 x sine 5x plus 1/25 cosine 5x plus c. Now you don't have time to do this, but if you had infinite time, you would take the derivative of this last line and you would get back to your original one.
Okay. Now, why did the 1/5 sine 5x? Why is there two 1/5s now?
So the first one is from that. This one comes from the antiderivative of sine 5x.
Okay.
And it's like you're really doing a u-substitution, but you don't do it unless you have to, like unless it's really unclear, you have to just account for it out here on the outside.
Okay.
Sometimes it's easier to say, like, is the derivative of 1/5 cosine 5x sine 5x? Yes, you'd say, oh yeah, multiply by 5, that cancels that. Derivative of cosine is minus sine, keep the 5x.
Okay. All right, another one. The integral of this is in parentheses x squared plus 2x cosine x.
So like, let me know if this is correct or not.
Yep, that's it.
Okay, so this is another one of these types where it's the integral of a polynomial of x times a sine, a cosine, or an e. And it is always the case that u is your polynomial. So in our case, u is going to be that x squared plus 2x. And then it is always the case that dv is the sine, cosine, or e. Like on your exam, it might be e to the x over here. So that means your dv, in the problem we're doing, your dv is the cosine x dx. So you got to take a derivative here, du, 2x plus 2 times dx. And then you're integrating on the right here, your V is sine X. And from here, you just remember your formula, uv minus the integral of v du. Have to remember that. Do you get a note sheet on this test?
Probably not.
Probably not. Okay. Yeah, so you better have this all down, those trig substitutions, partial fractions, all that fun stuff. So your uv here is x squared plus 2x times v sine x minus the integral of v, which is sine x times 2x plus 2 dx. And the order doesn't matter here. It doesn't matter that the sign's in front of this. Okay, so this thing that we're looking at now on the right, this is another integration by parts.
Right.
And I'm going to use u and dv again. It's common to do that. So u is going to be this 2x plus 2, and your dv is sine x dx. So we've got to find your du again. Du is 2 dx. You're integrating on the right here. Your v is minus cosine x this time. Let me know when you get caught up here to proceed.
Yeah. I'm good. I'm good.
Okay, so this you're subtracting this whole thing. So you're subtracting this uv minus integral v du. You're subtracting all of this now. And that means you're bringing this other stuff down. So it's x squared plus 2x sine x minus, okay, so you're minusing this uv. So you're minusing u times v. There's a negative there, so it's plus 2x plus 2 times cosine x. Sines are where a lot of students get messed up here. And normally it's minus integral v du, but you got a minus here. So it's like minus distributes in. So it's plus integral v du, but you got a minus there, so you have to change it back to a minus. And the more you can account for that, like as you go, the better.
Where does the plus 2x plus 2 cosine x?
That's uv. This is u. 2x plus 2 is your u.
Okay, right.
And your v is right there. You're just doing it again.
Okay.
Yeah. Okay, now this last one finally works out nicely. It's the antiderivative cosine is sine. So this becomes minus 2 sine x plus c. And then you bring everything else down to go along with it.
And the reason that the second UV is different is because it's the UV from the second integration by parts of the problem.
That's right. That's right. Yeah.
Okay. Right. All righty. I'm gonna grab another problem real quick.
Sounds good.
All right, this is okay. It's the integral of sine squared x cosine cubed x.
dx, right?
Okay, yep.
Okay, so I got to go find my reference here. Let me grab it.
This is trig intervals, right?
It's using yeah, let me get it here.
Like these are the ones where you, like if m is odd, then you do blah,
exactly.
blah, blah.
Exactly.
These are the ones that have the most.
That's what I'm looking for here. So we got
yeah, these are the ones I struggle with the most.
So you have to know, and the other ones are tangent secant. So I'm gonna snip the rules in
Right.
here. It's on that sheet I've sent you before. So if n is odd, which is not the case here, that's bad. If m is odd, strip one cosine out. Okay, so that means like you write you write a sine squared x, cosine squared x, cosine. Strip one cosine out and convert remaining cosines to sines. Okay, so it's saying instead of this cosine squared, make it 1 minus sine squared x. Okay, so if you follow that, it's so far it's sine squared x minus sine to the fourth x, because you multiply sine squared x by each of these times cosine x. And then your u is sine x. So this is not integration by parts. It's not a trig substitution. It's a product and some quotients of trig functions. It's really a u-sub problem, but it's they kind of do
I'm
this.
confused on the u-sub part of this.
Well, you can't do this at all. I mean, so we got to work through it. But like, are you okay up to this point?
Getting to this point, yes.
Yes. And you got to know this, 1 and 2 and 3 and 4.
So now, why is it sine 4?
Because you're multiplying instead of cosine squared x, you're writing it as 1 minus sine squared x, and then you're distributing this in. Okay, so your du is cosine x dx. Okay, so this becomes the integral u squared minus u to the fourth cosine x, but then your dx is du over cosine x. And that's the power of this method, is the cosines cancel. So you're just left with u squared minus u to the fourth du. So you get 1/3 u cubed minus 1/5 u to the fifth plus c, and then you back substitute your sine x in there. So it's 1/3 sine x to the third minus 1/5 sine x to the fifth plus c.
Okay. Well, in my notes, the m and the n are flipped.
Okay.
Like it's like the sine is m and the cosine is n. Does that matter?
No, you just got to learn the rules you like. But you can see here, there's like, here's one if n is odd, here's one if n and m is odd. It's if they're both odd, you can use either one, but when they're both even, that's another problem altogether.
Okay. Which one do you prefer to use if they're both odd?
I would have to do one to tell you.
Okay, I can give you one. I think this one is from a quiz we just took recently.
Okay.
Find it. Yep. It's tangent to the fifth x, secant to the third x.
Okay, so secant tangent is slightly different.
And dx.
Yeah. So here's the one. Here's the rule here. So if n is odd, strip one tangent and one secant out. So like I'm just going right for this. I don't if n is odd, we don't have that, and m is even. So since n is odd, since the one for tangent is odd, I'm just going to follow this to the letter here.
Oh, okay. So those aren't even. Oh, these rules are different. Okay.
Yes, they're slightly different. I don't even remember, like, I guess you got to know this now for this class, but I mean, it's just another, there's a lot of this in this class. So strip one tangent out, one secant out. So it's integral tangent times tangent to the fourth x secant times secant squared x, because that's the strip one tangent and one secant out.
All right.
Convert the remaining tangents to secants. Okay, so this secant squared becomes
Sorry.
convert the remaining tangents to secants. Sorry. Okay. Convert the remaining tangents to secant. Okay. So this is secant squared x minus 1 squared. And then use the substitution u equals secant x. Okay. I don't have a good feel for where this is going yet, but we'll just do it and we'll see.
Yeah, on the quiz I didn't either.
Okay, so
I'm pretty
du,
confused.
a derivative of secant is secant x, tangent x, dx. Okay, so how does that help here? Well, let's see here. So we got tangent x. This is u squared minus 1 squared. And then secant x, secant squared x, which we can deal with. But our du is, our dx is du over secant x tangent x. So here's what I see right now. I see that tangent and tangent cancel, secant and secant cancel. And this can be written as a u squared because it's secant squared. Gets you to
Right.
use. So you get integral u squared minus 1 squared u squared du. And this is still bad, but we can work with this.
So for these problems, using these rules, is it like purpose for to have the du over blah 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 whatever?
The du is just a function of just whatever the derivative is. You gotta.
No. Or like is the purpose of that to cancel out some of the
Yes,
some of the
almost
stuff?
always. Yes, almost always.
Okay, that's nice to know.
And that's why I didn't just start subbing in, secant is u and secant squared is u squared, because I don't know what's going to happen yet.
Uh-huh.
Okay, so now that we've gotten down to this line, you have to FOIL this, and then you have to multiply by u squared. So it's u to the 4th minus 2u squared plus 1 times u squared. We still have not integrated yet. U to the 6th minus 2u to the 4th plus u squared du. And then now it's just power rule. So it's 1/7 u to the 7th minus 2/5 u to the 5th plus 1/3 u to the 3rd plus c. And then your u is secant x. So we substitute that back in. 1/7 secant to the 7th x minus 2/5 secant to the 5th x plus 1/3 secant cubed x plus c.
All right. Alrighty. Next one is the integral of sine cubed theta cosine to the 4th theta d theta.
Right. So I'm very deliberate here in this part of the course because that's what we're got. So I'm just go back and grab these rules and I'm gonna just go down to the right one here. So it says if n is odd, which is what we have here, meaning the one above sine. The one above sine is odd. You strip one sine out. So when you strip it out here, you get sine theta, sine squared theta, cosine to the 4th theta, d theta. Then it says convert remaining sines. So this one here, using this. So this becomes 1 minus cosine squared theta, cosine to the 4th theta, like this. So it's the integral sine theta, okay, d theta. And then you have a choice here, like you probably are going to multiply this, but we can, I guess I can tell you that that's fine. Minus cosine to the 6th theta, d theta. And then it tells you your u is cosine theta. So your du is minus sine theta d theta, like you're asking for. So when you solve for d theta, it's du over minus sine theta. So when you sub in here, you get sine theta, u to the 4th minus u to the 6th. D theta is du over minus sine theta. And there's a cancellation there. This negative can come inside here to make this u to the 6th minus u to the 4th du.
Oh, okay, I get it. All right. Why wouldn't you put it just in front of the integral?
You could. It doesn't.
The
It's just a
same
choice.
thing.
Yeah.
Okay.
Okay, so that's 1/7 u to the 7th minus 1/5 u to the 5th plus c, and then you back substitute your cosine theta, and so 1/7 cosine to the 7th theta minus 1/5 cosine to the 5th theta plus c.
Okay.
If you have time on your own, obviously you could do all 4 variations on it, the ones that I've shown you. But you might be getting a feel for what your instructor tends to put on exams. You know.
Yeah, I'm about to find out now.
Yeah.
First exam. But she said she's gonna throw a bunch of integrals at us and not tell us which one, like how to do it.
Yeah, it's not going to say what it is. Yeah.
But I know everything that's gonna be on it.
Okay.
Could we do one with bounds now?
Sure. I mean, it's the same thing. You just end up plugging them in at the end. But yeah, absolutely.
All right. It's the integral from 0 to pi over 2.
Okay.
Sine to the 7th theta. Cosine to the 5th.
Like this.
Yep.
All right. So here they are both odd, both ones. So it says pick one. Doesn't really matter. So I guess you get to pick. Do you want to strip out a sine or a cosine?
Everybody's starting choosing to yell right now.
No problem.
Could you ask that again?
I was just the rule here says you can use either 1 or 2, which means you're either stripping out a sine or you're stripping out a cosine. Do you have a preference? Do you care?
I don't have a preference.
All right. So sine theta, sine 6th theta, cosine 5th theta, d theta.
Is this your preference, or you just go?
No, I didn't even think that. Just the first one.
Okay.
These are all the same. They're just long. So then it says if I strip a sine out, okay, I got to convert the remaining sines to cosine. So this right here is really sine squared theta cubed, which means it's 1 minus cosine squared theta cubed. Is that okay so far?
Yep, I'm with you.
Okay. Cosine to the 5th theta, d theta, sine theta, 0 to pi over 2. Now, the u is cosine theta. So your du is minus sine theta d theta. Because we're making a u substitution and we've got bounds, we can either choose to change the bounds or to wait until the end to put them back in. What do you normally do here in class?
My teacher does. She changes them now.
Okay, so to do that, you have to find u of 0, which is cosine of 0. And then you have to find u of pi over 2, which is cosine of pi over 2. You basically take each of these bounds and you plug them in here.
Okay.
So cosine of 0 is 1, cosine of pi over 2 is 0. So it ends up, and you got to be careful, it's 1 to 0, even though that seems wrong. That's what happens when you do this.
Okay.
So that's sine theta 1 minus u squared cubed. Okay. And then cosine to the 5th theta, and then d theta is du over minus sine theta. So the signs cancel. This negative, you asked me before, like this time we're going to put it out in front because we're gonna do something with it. Cosine is really u, so it's 1 minus u squared cubed times u to the 5th du.
Okay.
And then I'm going to flip the bounds here. So it's 0 to 1, and that consumes the negative.
Okay.
So as much as I don't want to do this, I guess my fastest path here is to just multiply this out.
Uh-huh.
And then you're going to multiply each one by u to the 5th. Okay, so we got 1 minus 2 u squared plus u to the 4th, and then 1 minus u squared over here. So then you got to do all of these. So it's 1 minus 2 u squared plus u to the 4th. And then we got minus u squared plus 2u to the 4th minus u to the 6th. So we got 1 minus 3u squared plus 3u to the 4th minus u to the 6th, all times u to the 5th. So it's u to the 5th minus 3u to the 7th plus 3u to the 9th minus u to the 11th du. So that's 1/6 u to the 6th minus 3/8 u to the 8th plus 3 over 10 u to the 10 minus u to the 12th over 12, evaluated from 0 to 1. Okay, so that's 1/6 minus 3/8 plus 3/10 minus 1/12. When you put in the top bound, the lower bound is 0. 60s are common denominator. No, 6 doesn't work with 8. Maybe it's 120.
We don't have to simplify, we can just leave it.
Great. Now that worked out nicely because the bounds changed from 0 to 1, which is why one reason to do the limits of integration change.
So instead of substituting the u to 6 with cosine,
yeah,
you do it with the bounds.
And what I'm saying is that if you're going to do the u, you change the bounds, and it often makes the problem simpler. So you should, like, you want to eventually like get to that point where you want to change the bounds,
right?
Especially when you see this in other classes.
I'm not understanding this last part.
Which part?
This two last parts.
So it's like starting this line right here.
No, to go down to
this one right here.
Yeah,
that's just power rule of u.
Right, and then how'd you get from that to the one below it?
You're just putting the top minus bottom bound in. So the top bound is 1. 1 to any power is always 1. So you don't even need you don't need to put in 1 to the 6th, 1 to the 8th, 1 to the 10th. It's just it's just the coefficients. Sorry, I did gloss right over that. 0 to any number is 0. So
you you just substitute the u's with the but the bounds.
Yes. Yes.
Okay.
Yes.
All right. All right. Now let me. We're having a blizzard coming over here, all the way over in Texas.
Yeah. So you see the news reports.
Uh-huh.
There was one last a big freeze, last February. I don't know if you were there back then.
Yep.
It was real bad.
And I'm getting an email. It's just saying it's gonna be delayed. School's gonna be delayed. Which is like that makes so much sense. Everywhere else is canceled, but not mine. It's just delayed.
Yeah.
All right. Partial fractions. I'm pretty confident with these.
Okay. Sometimes the instructor just asks you to set it up, but not to actually integrate.
Uh-huh.
So they want you to find the decomposition and then stop there. I see that a lot.
Yeah, I think that's how she that's how she does it. Let me just be for sure. If it's a case where like the degree of the numerator is bigger than the denominator, then she wants us to integrate after we long divide.
Yes. Yes. You got to remember to do that. That's like I don't know. It's like a remind, you got to know that stuff.
Yep, those are nice. I like those ones.
Yeah.
Oh, she does want us to. She integrated on that one. Yeah, she's wanting us to integrate. Integrate all the way.
Usually it turns into natural log or arctangent, or sometimes it's just a u-substitution.
Oh, I think for this little set of problems, it says write out the form of the partial fraction decomposition of the function. Do not determine the numerical values of the coefficients.
Yeah.
Does that mean just?
Yeah, they're like giving you most like this second line here, they'll give you like 2x plus 3 to the fourth, and they want you to write out all of these terms that might go with it.
Okay. Yeah, I'm pretty. Yeah, I can actually do that. I don't even need to go over this.
And they don't actually want you to solve because it takes too long. And they're actually supposed to teach this in college algebra, pre-calculus, but they don't seem to teach it.
Oh, really?
You get a review again here of it.
Yeah, we never did those in pre-calculus.
Good.
Can we do integral of 3t minus 2 over t plus 1?
Like this?
Yep.
Okay. All right. So the form on the bottom, term and partial. Oh, okay. So this one you can just write as 3t. I'm sorry, 3t over t plus 1 minus 2 over t plus 1. I'm not even sure this is a partial fractions problem.
It just says evaluate the integral.
Okay. So this one on the left is the tricky one. The one on the right here, I think probably could see that it's natural log absolute value t plus 1. This one on the left here, so let me just write it out. Integral 3t over t plus 1. If you make your u t plus 1, okay, your t, your du is dt, and you end up with this 3t over u times du. And you're like, hey, that doesn't work. You're right, but you can actually solve this. You can actually solve this for t.
Oh, okay.
So t is u minus 1. So it becomes 3 times u minus 1 over u, which doesn't look that great at first, but it actually works out really nicely. It's integral 3u over u minus integral 3 over u. There's a du there. Like it's 3u minus 3 over u, like that. And then on the left here, it just becomes the integral of 3 minus the integral of 3 over u du. So this is 3u minus 3 natural log absolute value of u. And then you can back substitute your t plus 1 in here. So it's 3 times t plus 1 minus 3 natural log absolute value t plus 1. And then come back to this other part over here, which we everything we just did was for this one. Was for, and so now it's minus 2 natural log absolute value of t plus 1 is the second part here. So you bring that down, minus 2 natural log absolute value of t plus 1, and you can actually combine these 3 t plus 1 minus 5 natural log absolute value t plus 1 plus c.
Okay.
But what's really critical is this thing here, though, that I did. It's a really common thing to like think that you can't do it and then get stuck. And you got to remember that you can sometimes solve for this variable again.
Right. All right. Let's do one that actually we can actually do it like the correct way. X over x squared plus x minus 2.
Like this. Minus 2, you said?
Yep.
Okay. So this is kind of your true partial fractions. The bottom factors, you want to do that right away. So you're looking for a over x plus 2 plus b over x minus 1. And do you have a preference for how to actually do this, or do you want to, like, there's many ways.
Like with systems of equations?
Well, like one way is to just multiply a by x minus 1 and b by x plus 2. That's kind of
we multiply both sides of it by the denominators.
Right. So it's a times x minus 1, b times x plus 2.
Right.
And that equals x. 1x.
With all those cancel out.
Yeah, so you're gonna get ax minus a plus bx plus 2b, 1x plus 0. And it's like you said, you get a system here. You get 1 equals a plus b, because those are the coefficients of x. And then you get 0 equals minus a plus 2b, because those are the non-x coefficients.
Okay.
And then you can solve like any way you want. Here you can actually just add them. So it's 1 equals 3b. So b equals 1/3. And then you can put that back in here. A equals 1 minus b, or 1 minus 1/3, which is 2/3.
Why can't you just add them together?
You can.
Why
can you? Oh, well, I'm sorry. That's a systems of equations technique.
Oh, okay.
If they're opposite sign, you just add them. and that's your
Okay.
shortcut. Now you got to be careful here that like I called A 2/3. A was this one in front. You know,
Right.
this is so it's like you got to go back and match them. So it was 2/3 over x plus 2 plus 1/3 x plus 1, and that was the integral x over what was this, x over x squared plus 2x minus 2,
Or
x
equals
minus
X
x
plus.
minus 2.
Yeah.
Yeah, like that. Okay, so that equals the integral of this. So this is the partial fraction is the hard part, because this is 2/3 natural log absolute value of x plus 2 plus 1/3 natural log absolute value of x plus 1 plus c.
Mhm. All right. We got like 4 minutes. I'm just gonna do one more of these and then we'll wrap it up.
Okay.
Let's do can we do one with bounds on them?
Sure. Yeah.
Actually, let me see. Right, okay. It's the integral of from 0 to 1 of 2 over 2x squared plus 3x plus 1.
Okay. So the bottom, you got to factor, as quickly as you can there.
Right.
So this becomes a over 2x plus 1 plus b over x plus 1. And then it's the same approach here. So it's a times x plus 1 plus b times 2x plus 1. This all equals 2. So it's 2 equals ax plus a plus 2bx plus b. This one has a 0x, which I'm writing just to kind of solidify that you set the x is equal. So a plus 2b. And then this other one, it's a plus b. So this time you can subtract. I would actually reorder it. I put 0 down here, and then I would subtract, because then you get a minus a is 0, b minus 2b is minus b, so b equals minus 2. And then maybe go back to, I don't know, that line there, and then a equals 4.
All right. And then just do the log and all that.
And then you evaluate the
Yeah.
a minus b. So it's like these are almost too easy to give you, but if they give you anything harder than this, then you got so many terms and you're solving,
Right.
3 equations, 3 unknowns. Like, I don't know. That's why sometimes it's just a setup problem. But if your instructor said, I'm going to have you do a bunch of these, you should be prepared to do one like this.
Yeah, there will be at least one. So
yeah.
Sometimes
What
do you do with the bounds?
Well, yeah. So let me get to where. So this a was 4, and b was minus 2. So you end up there's a bit more here to do this. Let me grab this line. Go down here. So we're just, come on, go down. There it is. So it ends up being the integral from 0 to 1, 4 over 2x plus 1 plus dx plus negative 2 over x plus 1 integral from 0 to 1 dx. Okay, so the one on the left here becomes 2 natural log absolute value of 2x plus 1. The reason is that normally it's that 4 is there, but when you integrate this 2x, you get it divides by 2, 0 to 1, minus 2 natural log absolute value of x plus 1 from 0 to 1. So it's 2 natural log of 2 times 1 plus 1 minus 2 natural log absolute value of 0 plus 1 And then on the right here, it's top minus bottom. So it's 2 natural log absolute value 1 plus 1 minus a minus 2 natural log absolute value of 0 plus 1.
Okay.
So you get 2 natural log of 5. This is natural log of 1, so it's 0 minus 2 natural log of 2. And then this is 0 because natural log of that. So you end up getting 2 natural log of 5 minus 2 natural log of 2. You could bring these back up, but it's unnecessary.
Mhm.
You get this far, your structure's pretty happy because analyzing the bounds there, but it's top minus bottom. It's always top minus bottom.
Okay. All right.
All right. Well, that does take us to the end of our lesson today. If you're gonna send some pictures for your physics lesson, just send them to me. And I've got Paul and I got a system that I send them over to him
Okay.
with.
I emailed them.
Oh,
sometime.
perfect. Yeah, email is always good, but if it's
I'll
faster
pass
snap
it.
pictures, it'll be much faster this time. We worked out some kinks.
All right.
Good luck on your exam and stay warm.
I appreciate it.
I'll see you next time. Have a great
All right.
night. Bye
You
now.
too.